In the vast tapestry of the cosmos, where mysteries unfold in every direction, we begin another journey of discovery. From the violent volcanic landscapes of Io to the familiar cratered face of our moon. From the intriguing atmosphere of the distant world K218b to the frozen terrains of Triton and the magnetic mysteries of Ganymede. Join us as we travel across the celestial wonders of our universe. As we venture beyond the worlds we know, we will explore places that may one day become the homes of future explorers. These enigmatic worlds challenge everything we think we understand about life, existence, and the nature of planets beyond Earth. As we dive deeper into the cosmic dance of gravity, ice, fire, and light, a profound question slowly emerges. Are we standing on the edge of discoveries that have remained hidden for millions, perhaps even billions, of years? Only time and space will tell. In the vast expanse of our solar system, among swirling gas giants and distant icy bodies, there exists a world so violent and so extreme that it challenges everything we once believed about planetary science. Welcome to Io, the volcanic wonder of the solar system. This distant moon of Jupiter may appear calm from afar, its surface painted in brilliant shades of red, orange, and yellow. Yet beneath that beauty lies a world in constant upheaval, a place where the ground itself rises and falls, and where the surface is continually reshaped by fire. Io is not a quiet celestial body. It is a storm of relentless change. Io, the third largest moon of Jupiter, is caught in a cosmic tug-of-war, a powerful gravitational dance with its massive parent planet and with neighboring moons such as Europa and Ganymede. This celestial ballet produces enormous tidal forces that cause Io's surface to rise and fall by as much as 330 feet. As the moon stretches and compresses under Jupiter's immense gravity, enormous amounts of heat are generated within its interior. This gravitational torment fuels the most spectacular volcanic activity anywhere in the solar system. Hundreds of volcanoes erupt across its surface. Some launch fountains of molten lava dozens of miles into its thin and nearly waterless atmosphere. Io is the most volcanically active world we know. Recently, stunning new observations from NASA's Juno spacecraft, during its 51st close flyby of Jupiter, revealed the fiery heart of Io in extraordinary detail. Glowing lava fields, immense volcanic calderas, and massive heat signatures scattered across the moon's surface. But these images are far more than beautiful photographs. They are scientific clues, small pieces of a much larger puzzle that may help us understand not only Io itself, but the forces that shaped our entire solar system. When we look at these fiery landscapes from our calm blue world, it reminds us just how diverse and extraordinary the worlds around us truly are. Our solar system is not a quiet collection of planets. It is a dynamic and evolving system filled with places of unimaginable energy and complexity. So come with us as we begin our journey to Io, the volcanic wonder of the solar system. Among scientists, the exact composition of Io's lava is still a matter of debate. Some theories suggest that it is composed largely of molten sulfur and sulfur compounds, while others propose that it is primarily silicate rock, similar to the volcanic material found on Earth. Although Io itself formed about 4.5 billion years ago, the surface we see today is astonishingly young. Most estimates suggest that Io's surface is no more than a few million years old. The reason is simple yet extraordinary. Continuous volcanic eruptions constantly renew the surface. Any impact craters left by meteorites are quickly buried beneath fresh lava flows, creating vast, smooth plains of newly solidified rock. One of the most fascinating features on Io is Loki Patera, the moon's most powerful volcano, This enormous volcanic depression is responsible for roughly 10% of the total heat emitted from Io's surface. Loki Patera remains one of the greatest volcanic mysteries in the solar system. Observations show that the brightness of this region increases and decreases in cycles, and scientists suspect that this pattern may be connected to subtle changes in Io's elliptical orbit around Jupiter. However, more data is still required before researchers can confirm this relationship with certainty. Interestingly, many of Io's brightest eruptions tend to occur on the trailing hemisphere of the Moon, the side facing backward relative to its motion around Jupiter. The reason for this uneven distribution of volcanic activity remains unclear. Even more puzzling is the fact that the locations of many volcanoes do not match the predictions made by existing tidal heating models. These inconsistencies add yet another layer of mystery to Io's already complex geology. The deeper scientists study Io, the more questions seem to appear, reminding us just how intricate and dynamic our solar system truly is. When we think of volcanoes, we often imagine the dramatic mountains that shape our own planet's landscape. From the explosive eruption of Mount St. Helens to the slow and persistent lava flows of Kilauea in Hawaii, Earth's volcanoes are powerful reminders that our planet is alive and constantly evolving. Yet, compared with Io, even Earth's most dramatic eruptions appear modest. On Io, volcanoes are not rare geological features. They are the rule rather than the exception. The immense gravitational pull of Jupiter, combined with the influence of neighboring moons, generates powerful tidal forces inside Io. These forces stretch and compress the Moon's interior, producing enormous amounts of heat and fueling constant volcanic activity. The scale and intensity of Io's eruptions dwarf anything we observe on Earth. The most active volcano, Loki Patera, is an enormous lava basin more than 125 miles across. During major eruptions, it can release enough lava to cover an area comparable to the U.S. state of New Jersey. By contrast, one of Earth's largest volcanic calderas, Mauna Loa in Hawaii, measures less than 4 miles across at its summit crater. The composition of Io's lava is also very different from that on Earth. While terrestrial volcanoes mostly erupt lava composed of silicate minerals, many scientists believe that Io's eruptions involve large amounts of molten sulfur and sulfur compounds. These materials are responsible for the Moon's striking yellow, orange, and red coloration. The surface of Io is essentially painted by sulfur chemistry on a planetary scale. Volcanic eruptions also affect planetary environments in very different ways. On Earth, massive eruptions can inject large quantities of ash and gases into the atmosphere, sometimes triggering temporary global cooling. On Io, however, the constant volcanic activity has produced only a very thin atmosphere composed primarily of sulfur dioxide. A dramatic example of Io's violent nature occurred in the year 2022, when astronomers observed an exceptionally powerful volcanic eruption. The event was so intense that it illuminated the enormous sodium cloud surrounding Jupiter, a structure connected to Io known as the Io plasma torus. This event served as a striking reminder of the extraordinary forces constantly reshaping this small moon. Yet these violent processes make Io even more fascinating to scientists. As the innermost of Jupiter's 4 Galilean moons, Io occupies a uniquely extreme environment. The ongoing gravitational tug-of-war between Jupiter and its neighboring moons drives volcanic activity that extends far beyond Io itself. Material blasted into space during eruptions does not simply fall back onto the moon. Some of it escapes Io's weak gravity entirely, forming a vast ring of electrically charged particles around Jupiter. This structure, known as the Io plasma torus, feeds energy into Jupiter's powerful magnetosphere, the region of space dominated by the planet's magnetic field. When particles from this torus interact with Jupiter's magnetic environment, they help produce brilliant auroras in the planet's upper atmosphere. Scientists are still studying the long-term consequences of Io's relentless volcanic activity. What is clear, however, is that the constant renewal of Io's surface dramatically shapes its geology and may even influence its potential to support certain forms of life. Io is, without question, the most volcanically active body in our solar system. Its surface is a hellish landscape continuously reshaped by hundreds of sulfur volcanoes erupting molten lava. The average surface temperature of the Moon is around -202 degrees Fahrenheit. While volcanic hotspots can reach an astonishing 2,900 degrees Fahrenheit, under such extreme conditions, it may seem impossible for life as we know it to exist. And yet life on Earth has proven to be remarkably resilient. Scientists have discovered organisms capable of surviving in environments once thought completely uninhabitable. These organisms are known as extremophiles. They thrive in places where most life would perish. From the crushing depths of the ocean to the boiling geothermal springs of Yellowstone National Park, some astrobiologists believe that if life does exist on Io, it would most likely be hidden beneath the surface. Despite the harsh radiation and extreme temperatures above ground, the subsurface environment could potentially offer shelter. Underground regions might protect organisms from Jupiter's intense radiation while providing enough heat and chemical energy for life to survive. One possible habitat could be lava tubes. These underground tunnels form when the outer layer of a lava flow cools and solidifies, while molten lava continues to move beneath the surface. On Earth, lava tubes are often home to microbial communities. Regardless of climate or geographic location, given Io's immense volcanic activity, similar structures may be common beneath its surface. If life did exist on Io, it would likely be very different from anything we know on Earth. Such organisms might rely on sulfur chemistry for energy, using compounds such as hydrogen sulfide instead of oxygen. In some theoretical models, hydrogen sulfide could even serve as a substitute for water in certain biochemical processes, since it can dissolve organic molecules and remain liquid under Io's subsurface conditions. For now, the possibility of life on Io remains purely speculative. However, scientists cannot completely rule it out. Future missions, including the proposed Io Volcano Observer, may eventually provide deeper insight into the Moon's interior and help determine whether any form of life could survive there. Looking ahead, our understanding of Io has improved dramatically thanks to ongoing exploration. NASA's Juno spacecraft, which has been orbiting Jupiter since the year 2016, has provided some of the most detailed observations of Io ever obtained. One of its key instruments, the Jovian Infrared Auroral Mapper, known as JIRM, has played an important role in revealing the Moon's volcanic activity. By detecting heat radiated in infrared wavelengths around 5 microns, the instrument allows scientists to map hotspots and active lava flows across the surface. These observations have enabled researchers to study Io's volcanoes in unprecedented detail. By observing the Moon during multiple flybys, scientists have been able to track how eruptions change over time, how frequently volcanoes erupt, how hot they become, and whether eruptions occur individually or in clusters. This growing body of data is helping scientists better understand the enormous flows of mass and energy within this extraordinary volcanic world. And it is paving the way for future discoveries about Io and the dynamic processes shaping our solar system. Research and discoveries continue to reveal more about Io, and the future holds very exciting prospects for exploring this extraordinary moon. Upcoming Juno flybys will bring the spacecraft even closer to Io, leading to twin flyby encounters when it passes a second time, just 900 miles above the Moon's surface. Such close encounters will provide an even more detailed view of Io's intense volcanic activity. In addition to Juno, The Jupiter Icy Moons Explorer, known as the JUICE mission, is expected to reach Jupiter by the year 2031. While JUICE's primary targets are the ocean worlds Europa and Ganymede, the data it gathers will inevitably deepen our understanding of the entire Jovian system, including Io. By the way, we have already explored some of these remarkable satellites in our previous videos. The scientific goals of these missions go far beyond simply observing Io and its volcanoes. They are designed to help scientists understand the deeper dynamics of our solar system. The data collected will help answer fundamental questions about how planetary bodies form and evolve. What kinds of environments might support life? And how powerful cosmic forces continue shaping our region of the universe. One particularly intriguing proposal is the Io Volcano Observer, often referred to as IVO. This mission has been designed to investigate Io in order to understand tidal heating as a fundamental planetary process. Its main objectives are to determine how and where tidal heat is generated inside Io, how that heat moves toward the surface, and how the Moon itself continues to evolve over time. The results of such research could have direct implications for the thermal histories of other worlds, including Europa and Ganymede. They may also provide valuable insight into other tidally heated bodies across the solar system, such as Triton and Enceladus. The mission concept treats Io as a planet-sized natural laboratory, a place where scientists can study processes that influence not only our own solar system, but also distant exoplanetary systems. If approved, the proposed baseline launch would place the spacecraft on a Mars-Earth gravity assist trajectory, often called a mega trajectory. Using the gravitational pull of both Mars and Earth, the spacecraft would gradually gain speed and eventually reach Jupiter in August of the year 2033. During the core mission phase, IVO would approach Io 9 separate times over a period of 4 years, allowing scientists to observe the Moon's dynamic surface again and again as its volcanoes reshape the landscape. Exploring Io, however, is not without challenges. The Moon's extreme volcanic activity and the intense radiation environment surrounding Jupiter pose significant risks to any spacecraft operating there. Yet with every challenge comes opportunity. An opportunity to push the boundaries of human knowledge, to innovate, and to discover. And while Io represents one of the most violent places in our solar system, our own Moon offers a very different kind of mystery. High above us in the night sky hangs a silent guardian, a constant companion that humanity has watched for thousands of years. The Moon, our Moon. For millennia, it has been a source of wonder and inspiration. It has served as a muse for poets, a guide for sailors, and eventually a destination for explorers. We have studied it, walked upon its surface, and even brought pieces of it back to Earth. Yet despite everything we have learned, the Moon still holds many secrets, continuing to captivate us with its mysterious appearance. Today we stand at the threshold of a new era in lunar exploration. The Artemis missions represent a bold venture that promises to take us farther than ever before, revealing truths that have been forming quietly over billions of years. Did you know that deep beneath the cratered surface of the Moon lies a solid iron core, or that water ice may be hidden within the permanently shadowed craters near its poles? And that is only the beginning. From stunning high-resolution images revealing the Moon's subtle natural colors to groundbreaking geological discoveries, we are learning more about our celestial neighbor than ever before. But before we look ahead to the future, it is worth taking a moment to look back into the past. The Moon has been part of human history since time immemorial, a constant presence in our night sky, inspiring both awe and curiosity. Ancient civilizations around the world revered the Moon, weaving it into their myths and legends. They carefully tracked its phases and created some of the earliest lunar calendars, systems that are still used in certain cultures today. The invention of the telescope in the 17th century marked a turning point in our study of the moon. Astronomers such as Galileo Galilei were able to observe the lunar surface with unprecedented detail. For the first time, humanity could clearly see the moon's mountains, its valleys, and its vast flat plains. Regions that early observers described as seas. Now let us move forward to the 20th century, to the era of the space race. When the Soviet Union launched Sputnik in the year 1957, it ignited a fierce technological rivalry between the world's superpowers. That competition ultimately culminated in NASA's Apollo program. In the year 1969, Apollo 11 made history. Neil Armstrong and Buzz Aldrin became the first humans to set foot on the surface of the moon, a moment that captivated millions of people around the world. The Apollo missions returned large collections of lunar rock and soil samples, along with enormous amounts of scientific data. These discoveries dramatically changed the way scientists understood the moon. Since that historic era, many additional missions from various countries have continued exploring our nearest celestial neighbor. We have mapped the moon's surface in extraordinary detail, discovered evidence of water ice, and studied its geology, its tenuous atmosphere, and even its weak magnetic field. More recently, the Artemis 1 mission has opened a new chapter in our journey of lunar exploration. Named after the twin sister of Apollo from Greek mythology, Artemis carries the torch of lunar exploration into the 21st century. Launched by NASA, Artemis 1 was an uncrewed test flight that sent the Orion spacecraft on a journey around the moon. The mission represented a crucial step in testing Orion's systems and capabilities, paving the way for future missions that will once again carry humans beyond Earth orbit. During its voyage, Orion traveled farther from Earth than any spacecraft built for human spaceflight had ever gone before. It completed a 6-day journey around the moon while collecting valuable data and testing its systems in the harsh conditions of deep space. The mission also provided breathtaking images of the lunar surface, captured by Orion's onboard cameras. These images revealed the stark beauty of the moon while also helping scientists and engineers better understand the performance of Orion's instruments and systems. After completing its journey, Orion returned to Earth, entering the atmosphere at speeds of around 20,000 miles per hour. The spacecraft successfully splashed down in the ocean, marking both the end of the mission and the beginning of a new era of lunar exploration. Artemis 1 stands as a testament to human ingenuity and the enduring spirit of exploration. It represents the combined effort of countless scientists, engineers, and visionaries working toward a shared goal, returning humans to the moon and eventually taking the next giant leap toward Mars. Our closest celestial neighbor is more than just a beautiful object in the night sky. It is a vast archive of information about the early solar system. Its geology preserves clues to its own fiery birth and its long, tumultuous history. The moon's surface is a rugged landscape of mountains, valleys, and plains, scarred by countless impact craters. Each of these features tells part of a story of ancient meteorite bombardments and the volcanic activity that once reshaped its surface. The rocks brought back by the Apollo astronauts revealed a great deal about the moon's composition. They showed that much of the lunar crust is made of basalt, a rock formed from lava that cooled rapidly after erupting onto the surface. And one of the most fascinating discoveries about the moon lies hidden deep beneath that surface. For many years, the nature of the moon's core remained uncertain, but recent research has begun to shed new light on its composition. Like the Earth, the moon has a layered internal structure, with a crust, a mineral-rich mantle, and a core. But unlike Earth's molten outer core, the moon's core is believed to be mostly solid. This conclusion comes from data collected by seismometers placed on the lunar surface during the Apollo missions. Those instruments recorded lunar tremors, or moonquakes, vibrations that travel through the moon's interior. By studying the way those vibrations move, scientists can infer the structure and composition of the moon's hidden inner layers, much like a doctor uses an X-ray to see inside a patient. This solid iron core is deeply important to our understanding of the moon's past. It suggests that the moon may once have possessed a magnetic field, generated as the iron in its interior gradually cooled. That ancient magnetic field may have helped shield the lunar surface from solar radiation. Much as Earth's magnetic field protects our planet today, a solid iron core may also help explain part of the moon's volcanic history. As the core cooled and solidified, the moon itself would have contracted. That shrinking released internal heat and may have triggered volcanic eruptions. Eruptions that helped shape the lunar surface, forming broad plains and filling ancient impact basins with lava. And perhaps most importantly, the existence of a solid iron core gives us insight into how the moon itself was formed. It supports the long-standing theory that the moon was born from the debris of a colossal collision between the young Earth and a Mars-sized body. Such a violent beginning would have left the moon covered by a global ocean of molten rock, which slowly cooled and solidified over billions of years to become the world we know today. And yet, even now, the moon continues to surprise us. The more closely we study our nearest celestial neighbor, the more mysteries seem to emerge. Every layer of the moon, from its battered surface to its hidden core, has a story to tell. And then there is water. Water, the very foundation of life as we know it. For a long time, scientists assumed that the moon, with its barren and airless surface, was completely devoid of it. But recent discoveries have overturned that assumption. As we know, the moon's surface is covered in countless craters. Near the poles, many of these craters lie in permanent shadow, untouched by sunlight and protected from the sun's warmth. In those eternally dark regions, temperatures can fall to as low as -418 degrees Fahrenheit, cold enough to trap water ice for billions of years. Several missions have now found evidence of that ice. NASA's Lunar Reconnaissance Orbiter, or LRO, has played a major role in this discovery. Since the year 2009, LRO has been creating highly detailed maps of the lunar surface, and its data has revealed signs of ice in craters near the poles. Another mission, the Lunar Crater Observation and Sensing Satellite, or LSCROSA, provided dramatic confirmation in the year 2009. In that mission, a spent rocket stage was deliberately crashed into a crater near the moon's south pole. The impact sent a plume of debris high above the surface, and that material was analyzed by the trailing spacecraft. The results revealed a significant amount of water ice. That discovery alone was a major breakthrough. But more recent research has taken our understanding even further. A later study produced a detailed map showing how water may be distributed near the moon's south pole. This map was created using data from NASA's Stratospheric Observatory for Infrared Astronomy, known as SOFIA, together with data from the Lunar Reconnaissance Orbiter. It revealed something important. Water on the moon is not spread evenly across the south polar region. Instead, it appears to be concentrated in specific craters and localized regions. That raises even deeper questions. Where did this water come from? Is it ancient, locked away in lunar minerals since the moon's early volcanic past? Was it delivered by asteroids or comets? Or perhaps by interactions with the solar wind? And once it arrives, does it migrate across the surface over time? These questions remain open, and Sophia's observations have only made the mystery more fascinating. Still, this map of lunar water is more than just a scientific milestone. It is also a practical guide for the future of exploration. Knowing where water exists on the moon is crucial for planning future missions, especially those aimed at establishing a lasting human presence there. Water is one of the most valuable resources in space. It can be used for drinking, for growing food, and for providing oxygen to breathe. But perhaps most importantly, it can be separated into hydrogen and oxygen, the very components needed for rocket fuel. In other words, water on the moon could one day be used to refuel spacecraft. That possibility turns the moon into something more than a destination. It turns it into a potential refueling station for deeper missions into the solar system, including missions to Mars. And yet, water is not the only hidden surprise the moon has to offer. When most people think of the moon, they imagine a barren, airless world. But the moon does, in fact, have an atmosphere. Though atmosphere may be too generous a word, what the moon has is an exosphere, the thinnest kind of atmosphere possible. It is so incredibly rarefied that individual particles almost never collide with one another. Instead, they move in ballistic trajectories, like tiny projectiles briefly leaping above the surface before falling back again. The lunar exosphere contains gases such as helium, neon, and argon, along with traces of other elements. Many of these particles are released from the lunar soil through a process known as degassing. NASA's Lunar Atmosphere and Dust Environment Explorer, or LADEE, was launched in the year 2013 specifically to study this fragile envelope. The mission made detailed measurements of both the composition and structure of the exosphere, as well as the behavior of lunar dust. One of the mission's key discoveries was the detection of a dust cloud hovering above the moon's surface. This dust is lofted upward by tiny micrometeorite impact, creating a temporary and constantly changing dust exosphere. Understanding this exosphere will be essential for future lunar missions. It could affect landing and takeoff conditions, and in some cases may even pose a hazard to astronauts and equipment operating on the surface. As our scientific understanding of the moon has grown, so too has our ability to see it in astonishing detail. From the earliest photographs taken by lunar orbiters to the extraordinary high-resolution images captured by modern telescopes and spacecraft, the moon has gradually revealed itself to us with increasing clarity. Craters, mountain ranges, valleys, and plains now appear in remarkable detail. One of the most extraordinary lunar portraits in recent years was created by astrophotographers Andrew McCarthy and Connor Mathern. This was not a single photograph, but a massive composite made from more than 200,000 images captured over the course of a single evening and then carefully stitched together. The final result was breathtaking. A lunar mosaic of extraordinary detail, assembled tile by tile, with each tile made from thousands of individual frames. This method, known as stacking, increases the signal-to-noise ratio, improves clarity, and reduces the blurring effects of Earth's atmosphere. The finished image became a stunning 174-megapixel portrait of the moon, revealing virtually every crater, ridge, valley, and subtle tonal variation across its surface. Those delicate color differences are not artistic exaggerations. They reflect real variations in the composition of lunar soil. Creating an image like that is no simple task. It requires advanced equipment, stable skies, precise alignment, and many hours of image processing. But the result is worth every effort. Images like these are not only beautiful, they are scientifically valuable, helping researchers study lunar geology, monitor surface features, and plan future missions. And as we look ahead, one mission in particular stands out as the next major step in humanity's return to the moon. That mission is Artemis 2. Artemis 2 is the next major chapter in NASA's lunar program, and it will be the first crewed mission around the moon in the 21st century. It is designed to carry astronauts on a journey beyond low Earth orbit, around the moon, and safely back home again. The crew represents a historic milestone. It includes the first woman and the first person of color ever assigned to a lunar mission. NASA astronaut Reed Wiseman will serve as commander. Victor Glover will be the pilot. Canadian Space Agency astronaut Jeremy Hansen and NASA astronaut Christina Hammock-Koch will also join the mission. The goals of Artemis 2 are ambitious. It will be a multi-day mission and a critical test of both the Orion spacecraft and the Space Launch System rocket, paving the way for future lunar landings. But perhaps its greatest significance lies in something deeper. Artemis 2 will revive the human experience of voyaging beyond Earth for the first time in roughly 5 decades. And yet, Artemis 2 is only the beginning. It is part of a much larger plan to establish a sustained human presence on the Moon. Future Artemis missions will aim to land astronauts on the lunar surface, build the technologies needed for long-duration exploration, and learn how to use local resources to support human life beyond Earth. The Moon, in that sense, is more than a destination. It is a proving ground, a place where we can develop the systems, strategies, and habits required to explore the solar system more deeply. It is where we can begin learning how to live off Earth. So as we stand at the threshold of this new era of lunar exploration, we are not only looking at the Moon, we are looking beyond it, toward Mars and toward the distant worlds that still wait for human arrival. And on that long journey, the Moon is our first step, a beacon lighting the way to the stars. In the grand theater of the cosmos, few relationships are as intimate and consequential as the relationship between Earth and its natural companion, the Moon. That bond began more than 4.5 billion years ago, and it has helped shape the fate of our planet ever since. The Moon orbits Earth at an average distance of about 238,857 miles. It is the 5th largest moon in the solar system, and relative to the size of its planet, it is among the most significant. As it circles Earth, we see changing portions of its sunlit half, creating the familiar phases of the Moon. And when the Moon moves into Earth's shadow, we witness a lunar eclipse, one of the sky's most captivating spectacles. The Moon also drives Earth's tides. As it orbits, its gravity pulls on our oceans, creating bulges of water that produce 2 high tides and 2 low tides each day. In a broader sense, the Moon has also served as a kind of shield. Many of the craters covering its surface are scars from impacts that might otherwise have struck Earth. But perhaps its most profound role has been in shaping life itself. The Moon helps stabilize the tilt of Earth's axis, which in turn helps maintain a relatively stable climate over long periods of time. That stability may have been crucial for the development of complex life on our planet. So when we explore the Moon, whether through telescopes, robotic probes, or missions like Artemis, we are not only learning about our nearest celestial neighbor, we are also learning about Earth, about our own history, and about the fragile conditions that made life possible here. And from that familiar companion in our own sky, our story now moves outward, far beyond the Earth-Moon system, toward a distant world that may force us to confront one of humanity's oldest and most unsettling questions. Are we alone in the universe? The James Webb Space Telescope may have brought us one step closer to an answer. Meet K218b, a distant exoplanet that has suddenly moved to the forefront of astrobiological research. Why? Because James Webb has detected something unusual in its atmosphere. Something that could, at least in principle, point toward the presence of life. Water vapor, methane, And even the rare molecule dimethyl sulfide are not just random chemicals. They may be biosignatures, clues that some form of life could exist beyond Earth. Armed with some of the most advanced space technology ever built, James Webb has become our new eye on the deep universe. A telescope designed to peer into the unknown and perhaps reshape our understanding of life itself. So are you ready to leave the familiar worlds of our solar system behind and step into the mysterious realm of K218b? As we push deeper into space and continue searching for answers to questions that have haunted humanity for generations, we rely on extraordinary instruments to bring the universe into focus. One of the greatest of them is the James Webb Space Telescope, often abbreviated as JWST. For decades, the Hubble Space Telescope served as humanity's window into the cosmos, producing images that both inspired and informed us. But even Hubble has its limits. James Webb was built to go further. One of its most remarkable features is its enormous multi-layered sunshield, a feat of engineering roughly the size of a tennis court. This shield blocks heat from the Sun, Earth, and Moon, allowing the telescope to cool to extraordinarily low temperatures. That extreme cooling dramatically increases its sensitivity to faint infrared signals coming from distant worlds. This matters because infrared observations are especially important for studying exoplanets such as K218b. Visible light can be scattered or blocked by dust, but infrared wavelengths can pass through far more effectively, giving us a clearer view of distant planetary systems. James Webb's infrared vision is not merely an upgrade. It is a revolution in the way we study worlds beyond our own. And when we turn that vision toward K218b, the picture becomes even more intriguing. Located about 124 light-years away in the constellation Leo, K218b is not just another distant planet. It lies within what astronomers call the habitable zone, the region around a star where temperatures may allow liquid water to exist. But what makes this world especially fascinating is that it may not be rocky like Earth at all. Instead, scientists believe it may belong to a class of planets known as Hycean worlds. Hycean worlds are thought to have hydrogen-rich atmospheres and vast global oceans beneath them. They represent an entirely new frontier in the search for extraterrestrial life. Because their conditions may resemble environments around hydrothermal systems on Earth, places where life can flourish even in darkness and extreme conditions. Recent observations from the James Webb Space Telescope have revealed a compelling mix of molecules in the atmosphere of K218b. Water vapor, methane, and even tentative signs of dimethyl sulfide. Together, these gases create a chemical picture that is difficult to ignore. It is the atmospheric fingerprint of a world that may be far more interesting than anyone expected. A world that could potentially support life, or at least forms of chemistry that push us to rethink what life might look like beyond Earth. The discovery of these atmospheric components has sent a wave of excitement through the scientific community. Researchers are energized not only by what has been detected, but by what those detections might mean for astrobiology and for the larger question of how life emerges in the universe. Could this Hycean world, with its unusual atmosphere and possible ocean beneath, become the key to unlocking the mystery of extraterrestrial life? And if so, what might its strange environment teach us about the future of astrobiology itself? When we enter the field of exoplanet exploration, one of the most difficult and yet most rewarding challenges is the study of alien atmospheres. K218b offers a compelling example. Earth's atmosphere is dominated by nitrogen and oxygen, with smaller amounts of other gases mixed in. K218b appears to be something very different altogether. Its atmosphere seems to be rich in hydrogen, with traces of water vapor, methane, and perhaps even dimethyl sulfide. That combination makes it a world of extraordinary scientific interest. But studying the atmosphere of a planet more than 100 light-years away is no simple task. It requires a method known as spectroscopy. In this technique, scientists analyze the light from the host star as it passes through the planet's atmosphere. Different molecules absorb light at specific wavelengths, leaving behind a pattern, a kind of chemical fingerprint, that can be decoded to reveal the atmosphere's composition. The infrared capabilities of the James Webb Space Telescope have been central to this effort. Its instruments can observe wavelengths that were previously difficult or impossible to study in such detail, allowing scientists to search for molecules that might otherwise remain hidden. That is why James Webb has become so important in the search for biosignatures on distant worlds. One especially intriguing detail is the presence of methane alongside the apparent lack of ammonia in the atmosphere of K218b. That combination has led scientists to wonder about the kinds of chemistry, or perhaps even biology, that might be possible there. On Earth, methane is often associated with biological activity, although it can also be produced by non-biological processes. Still, its presence on this distant world raises the possibility of life forms adapted to a hydrogen-rich environment. Something unlike anything we have yet observed directly. The composition of the atmosphere also hints at something even more tantalizing beneath it. Some researchers believe it may point to the existence of a subsurface or deep global ocean. If that is true, then K218b becomes even more fascinating, because it raises questions about how an atmosphere and an ocean might interact, and whether those interactions could make the planet more hospitable to life. And that leads us to an important shift in perspective. When most of us imagine life, we imagine Earth-like conditions, mild temperatures, liquid water on the surface, a breathable atmosphere. But life on Earth has already shown us that those assumptions may be far too narrow. Some of the most remarkable organisms on our own planet live in environments that once seemed utterly uninhabitable. These organisms are known as extremophiles. They thrive in places of crushing pressure, extreme heat, intense acidity, or complete darkness. Deep beneath Earth's oceans, hydrothermal vents release superheated mineral-rich water into the surrounding blackness, creating ecosystems that flourish without sunlight. Organisms such as thermophiles and acidophiles survive there, forcing us to rethink what life truly needs in order to exist. Could similar forms of life exist on K218b? Its hydrogen-rich atmosphere offers conditions unlike those on Earth's surface, but not necessarily beyond the reach of biology altogether. On our own planet, certain microorganisms, known as methanogens, produce methane in oxygen-free environments. If methane on K218b were being produced biologically, it might suggest a world inhabited by hydrogen-loving extremophiles, organisms adapted to a chemistry very different from our own. The study of extremophiles has dramatically expanded the range of environments in which scientists think life might survive. From the acidic waters of Rio Tinto in Spain to the frozen tundra of Siberia, life has proven again and again that it is more adaptable than we once believed. That diversity encourages us to widen our view of what extraterrestrial ecosystems might look like. This is why K218b has become such an attractive target in the search for life beyond Earth. A possible ocean below and a hydrogen-rich atmosphere above create a combination that may support forms of life adapted to extreme planetary conditions. And if such life exists there, one cannot help but wonder how it might evolve over time. On Earth, life began with simple single-celled organisms and gradually developed into more complex forms. Could something similar unfold on other worlds? Given enough time, enough energy, and the right chemical conditions. One of the most fascinating aspects of K218b is the possible presence of dimethyl sulfide, often shortened to DMS, on Earth. This compound is commonly produced by marine phytoplankton and is therefore considered a potential biosignature. It also plays ecological roles in our own atmosphere, including processes linked to cloud formation. If dimethyl sulfide truly exists in the atmosphere of K218b, it could become one of the most significant clues yet discovered in the search for alien life. But this is where the story becomes more delicate. The possible detection of DMS is still being tested. James Webb is capable of identifying complex molecules through infrared spectroscopy. But confirming a result like this requires careful analysis, repeated observation, and expert interpretation. In other words, this is not the kind of discovery scientists can afford to rush. Naturally, the possibility has generated both excitement and caution. As with many major scientific findings, the response has been divided between optimism and skepticism. Some researchers see DMS as a strong biosignature candidate. Others warn that non-biological processes might also produce similar molecules under certain conditions. That disagreement does not weaken the science. In fact, it strengthens it. Because skepticism is not the enemy of discovery. It is part of the method that protects discovery from error. History reminds us of this again and again. When Galileo first reported the moons of Jupiter, many resisted his claims. When the first exoplanet was discovered in the year 1995, scientists responded with careful caution rather than immediate certainty. That pattern is not a flaw in science. It is one of the reasons science works. The search for extraterrestrial life will not be solved by a single molecule or a single observation. Scientists are looking for patterns, combinations, and converging lines of evidence. Water vapor alone is not enough. Methane alone is not enough. DMS alone is not enough. But together, these signals may begin to form a more compelling picture. So the real question is not simply whether DMS is present. The deeper question is whether it is part of a larger atmospheric puzzle. One that includes methane, water vapor, and other chemical markers that together point toward biology rather than chemistry alone. That debate will likely continue until more data arrives. And as technology advances, future missions with even more sensitive instruments may provide the confirmation needed to determine whether DMS is truly a biosignature, or simply another reminder of how inventive nature can be without life. Either way, the discussion itself is valuable. It shows us science in motion, careful, uncertain, curious, and always willing to revise its conclusions in the light of new evidence. And perhaps that is what makes this moment so compelling. We may not yet have the answer, but for the first time, we may be learning how to ask the question in the right way. The James Webb Space Telescope has already revolutionized our understanding of exoplanets, such as K218b. But in reality, it represents only one step in a much longer journey of discovery. The deeper question is what comes next, and how future technologies will continue expanding our view of the cosmos. One of the most anticipated instruments is the extremely large telescope, scheduled for completion in the coming years. With a primary mirror measuring roughly 128 feet in diameter, it will become the largest optical and near-infrared telescope ever built on Earth. Its extraordinary sensitivity could allow astronomers to confirm or challenge the possible biosignatures first hinted at by the James Webb Space Telescope. Another concept under discussion is the Large UV Optical Infrared Surveyor, often referred to as LUVOIR, designed to observe across a very wide range of wavelengths. This mission could complement Webb's discoveries by providing even more precise atmospheric measurements and, potentially, the first direct images of distant exoplanets themselves. As our targets move farther into interstellar space, advances in propulsion technology will also become increasingly important. Concepts such as ion propulsion, already used on several deep space missions. And more speculative ideas like antimatter propulsion could one day shorten travel times dramatically. In theory, such technologies might even allow probes to reach nearby star systems within a human lifetime. We explored some of those possibilities in one of our earlier videos on interstellar travel and the enormous challenges that still stand in the way. Standing at the edge of such potentially transformative discoveries, it is worth pausing for a moment to consider the deeper questions that drive our curiosity. What would the discovery of extraterrestrial life mean for our understanding of existence? And what new questions might arise once that discovery is made? One topic receiving growing attention is the role of red dwarf stars in our galaxy. These small, dim stars are far more numerous than larger stars like our Sun, and many of them remain stable for extraordinarily long periods of time. Could such long-lived stars host planets where life has had billions of years to emerge and evolve? And what would it mean if we discovered something as simple as extraterrestrial phytoplankton? Even microscopic life beyond Earth would change our understanding of biology forever. It would suggest that the chemical ingredients of life are not unique to our planet but may be widespread throughout the universe. So, what will the coming decade reveal? Will we finally confirm that life exists beyond Earth? Or will we uncover even deeper mysteries that challenge everything we thought we understood about the cosmos? As we search for answers among distant stars and planets, another mystery waits much closer to home. Hidden in the outer reaches of our own solar system, far beyond the orbit of the giant planets lies an icy world wrapped in darkness. Neptune's mysterious moon Triton. At first glance, Triton appears silent and frozen. But this distant satellite hides features that continue to puzzle scientists. Unlike most moons in the solar system, Triton orbits Neptune in the opposite direction of the planet's rotation. This unusual retrograde motion suggests that Triton may not have formed around Neptune at all, but was instead captured by the planet's gravity long ago. Its surface is also surprisingly young. Occasionally, it even displays eruptions of cryovolcanic material, icy plumes that hint at hidden activity beneath the frozen crust. And beneath that ice, some scientists suspect that a deep subsurface ocean may exist. A hidden environment where entirely unfamiliar forms of life might potentially arise. To understand Triton, we first have to understand its distant parent world, Neptune. The deep blue giant swept by powerful winds is one of the most remote planets in our solar system. Excluding Pluto, it is the most distant major planet from the Sun and is far too dim to be seen with the naked eye. 14 known moons orbit Neptune. But Triton is by far the most unusual of them. Triton was discovered in the year 1846 by the British astronomer William Lassell, shortly after Neptune itself had been identified. Remarkably, Neptune was discovered not through direct observation but through mathematical calculations predicting its gravitational influence on other planets. From the moment Triton was first observed, astronomers realized it was different. Most moons orbit their planets in the same direction that the planet rotates. Triton does the opposite, traveling in a retrograde orbit that immediately suggested a very different origin. Scientists soon noticed that Triton shares many similarities with the dwarf planet Pluto. Their sizes, mass, and even the composition of their surfaces appear strikingly similar. This resemblance has led researchers to suspect that Triton may once have been a free-wandering object from the Kuiper Belt before Neptune captured it. The moon's diameter measures about 1,680 miles, making it nearly 7 times larger than Neptune's second largest moon, Proteus. Because of its size, Triton is able to hold onto a thin atmosphere composed mainly of nitrogen with traces of methane. Even more intriguing, the upper layers of that atmosphere contain an ionosphere, a region where atoms and molecules become ionized by radiation. In some ways, this ionosphere appears even more active than Earth's. These characteristics strengthen the idea that Triton may resemble an icy dwarf planet more than a typical moon. The ratio of rock to ice within Triton is estimated to be roughly 70% rock and 30% ice. That composition hints at a complex interior structure. Scientists suspect that Triton, much like Earth, may contain a layered interior consisting of a crust, a liquid mantle, and a rocky core. Yet, Triton remains one of the coldest places in the solar system. At a distance of nearly 2,793,000,000 miles from the Sun, the average surface temperature falls to around -400 degrees Fahrenheit. Its surface is coated in frozen nitrogen, beneath which lies a thick mantle of water ice. The bright, icy crust reflects nearly 70% of the sunlight that reaches it, giving Triton a brilliant, reflective appearance. Despite these extreme conditions, Triton does not appear to be a dead world. Its surface shows signs of recent geological activity. Many of its impact craters are surprisingly shallow and small, suggesting that the surface has been resurfaced over time. In other regions, scientists have observed long ridges and valleys forming strange patterns that resemble the skin of a melon. Dark streaks stretch across parts of the surface, patterns that cannot easily be explained by meteorite impacts alone. If collisions were the only process shaping Triton, its surface would likely be covered in far larger and deeper craters. Instead, astronomers suspect that a hidden ocean may lie beneath the icy crust. The surface may be continuously refreshed by mixtures of water and nitrogen ice rising from below. But how does water reach the surface on such a frozen world? There are two possible explanations. Water may be exposed when meteorite impacts fracture the surface, or it may erupt from within the moon itself through cryovolcanic activity. Evidence for cryovolcanism also appears in Triton's remarkable nitrogen polar caps. These features may form when subsurface material erupts upward and freezes again on the surface. But this raises another question. How can eruptions occur on a world so cold? One possible answer lies in Neptune's powerful gravitational pull. As Triton orbits the planet, gravitational forces constantly stretch and compress the moon's interior. This process, known as tidal heating, can generate internal warmth that melts pockets of ice beneath the crust. In addition, sunlight can penetrate the translucent surface layers of nitrogen ice, warming subsurface pockets of gas until pressure builds and eventually bursts through the surface. Some of these eruptions may continue for more than a year, sending plumes of nitrogen and icy material high above the surface before the debris settles back down. Heidi Hummel, a senior researcher at the Institute of Space Science, has suggested that such powerful geysers may require a significant internal heat source and perhaps even a subsurface ocean. However, the existence of such an ocean has not yet been confirmed. There are still several competing explanations for Triton's unusually young surface. Internal heat could melt pockets of nitrogen ice that then erupt outward. Or cryovolcanoes may be fueled not by a deep ocean, but by smaller reservoirs of water trapped within the crust. Ultimately, Triton raises more questions than answers. And the only way to resolve those questions is through new missions to the distant frontier of the solar system. So far, only one spacecraft has ever visited this mysterious moon. In the year 1989, Voyager 2 flew past Neptune and Triton during its historic journey through the outer solar system. As it passed over Neptune's north pole, the spacecraft used the planet's gravity to bend its trajectory toward Triton, approaching the moon at a distance of roughly 25,000 miles, comparable to the altitude of geostationary satellites above Earth. During that brief encounter, Voyager 2 captured the first detailed images of Triton's surface before continuing its journey outward into deep space. Those images transformed our understanding of the moon. Thanks to Voyager's observations, scientists were able to determine Triton's mass, analyze its atmosphere, and begin piecing together the complex story of this distant and enigmatic world. For example, it was the Voyager 2 mission to Triton that first established that the Moon's atmosphere is dominated by molecular nitrogen, with only a small amount of methane mixed in. This discovery immediately suggested that Triton might be geologically active and led scientists to investigate the mysterious eruptions observed on its surface. Voyager 2 also demonstrated that Triton does not contain oceans of liquid nitrogen on its surface, while revealing extraordinary details about the Moon's icy terrain. However, the spacecraft managed to observe only about 40% of Triton, mainly its southern hemisphere and only one side of the Moon, because Triton always keeps the same face turned toward Neptune. Nearly 33 years after Voyager captured the first close images of Triton, the James Webb Space Telescope produced a new and equally striking view of Neptune and its largest moon. Though from a much greater distance, Webb revealed Neptune's faint ring system and several of its moons. But the brightest object in the image immediately drew attention. To the left of Neptune appears what looks like a brilliant star. Yet this bright point is actually Triton itself. Its intense brightness confirms the presence of a surface coated with condensed nitrogen ice, which reflects a large portion of the sunlight that reaches it. Although the images collected over the past 3 decades have dramatically improved our knowledge of Triton, they are still far from enough to produce a complete global map of the Moon or answer the many questions that remain. That is why scientists continue to argue that new missions to Triton are essential if we want to understand this distant world fully. One of the most fascinating aspects of Triton is its unusual orbit. As mentioned earlier, Triton moves in the opposite direction of Neptune's rotation, a retrograde orbit that is extremely rare in the solar system. Only a few satellites across the entire planetary system display this kind of motion. Triton's orbit is also tilted by about 23 degrees relative to Neptune's equatorial plane. Such unusual motion is often associated with past gravitational disturbances or collisions with other objects. At one time, scientists considered the possibility that Triton had collided with another body in the distant past, which might have reversed its motion. However, this explanation has gradually fallen out of favor because it does not fully account for Triton's large size and its strong similarities to dwarf planets like Pluto. A more convincing explanation lies much farther from Neptune. The planet's orbit lies close to the outer boundary of the Kuiper Belt, a vast region filled with icy remnants from the early solar system. Pluto itself resides in this region, along with many other frozen bodies. Astronomers now believe that Triton may once have been an independent object from this distant belt. According to this idea, Triton was originally part of a binary system, somewhat similar to the Pluto and Charon pair. As this system passed near Neptune, the planet's powerful gravity disrupted the pair. Triton was captured into orbit around Neptune, while its former companion may have been flung outward and possibly even ejected from the solar system altogether. Neptune's gravity would have reshaped the entire satellite system during this capture event. Today, Triton contains about 99.5% of the total mass of all the objects orbiting Neptune. Such dominance suggests that Triton's arrival may have destroyed or scattered many of Neptune's original moons, leaving behind only small fragments that later reassembled into the satellites we see today. The remaining moons of Neptune are usually divided into 2 groups: inner and outer satellites. Most of them are extremely small compared with Triton. Some of the outer moons may also have been captured objects, much like Triton itself. Triton's influence can even be seen in the strange orbit of the moon Nereid. Nereid follows an extremely elongated path around Neptune. At its closest point, it approaches about 88,500 miles from the planet, while at its farthest point, it can travel nearly 6 million miles away. Scientists suspect that Triton's migration through the Neptunian system may have disturbed Nereid's orbit long ago, pushing it into this unusual trajectory. Because Triton orbits Neptune in a retrograde direction, it is slowly losing orbital energy over millions of years. Tidal interactions will gradually pull the Moon closer to Neptune. Eventually, Triton may cross the planet's Roche limit and be torn apart by Neptune's gravitational forces, forming a new ring system around the planet. That dramatic outcome, however, lies millions of years in the future. For now, Triton continues to intrigue scientists with another possibility: the existence of a hidden ocean beneath its frozen crust. Despite being covered in condensed nitrogen ice, the Moon's interior may contain liquid water warmed by tidal heating. If such an ocean exists, it could potentially provide an environment where simple life might arise. Water plays a central role in nearly all biological processes known on Earth. It provides the medium for chemical reactions, helps maintain cellular structures, and supports the complex interactions required for living systems. Voyager 2 also detected dark cryovolcanic plumes erupting from Triton's surface during its flyby. One of the most unusual plumes appeared almost black and rose roughly 5 miles above the surface. Scientists believe this dark color may be caused by carbon-rich material mixed into the erupting gases. Carbon is the fundamental building block of life, forming the backbone of organic molecules, from the simplest compounds to the complex chemistry of living organisms. Although scientists cannot yet determine the precise composition of Triton's hypothetical ocean, some researchers at the American Astronomical Society have suggested that its chemistry could resemble that of icy comets. In such a scenario, the ocean might contain ammonia, sodium chloride, oxygen compounds, and other volatile substances. Even so, Triton remains an extremely cold world. Temperatures are so low that complex life similar to that on Earth would be highly unlikely. The Moon's thin nitrogen atmosphere is far too weak to trap significant heat, and even clouds of nitrogen ice cannot provide meaningful warming. Yet Triton does experience seasonal changes. Observations made with the Very Large Telescope of the European Southern Observatory revealed that the Moon's climate shifts over time, though its seasons last far longer than those on Earth. Instead of 3-month seasons, Triton's seasons can extend for roughly 40 years. At present, Triton appears to be in a summer phase. Researchers from the Massachusetts Institute of Technology have observed a slight temperature increase, rising from about -392 degrees Fahrenheit to roughly -389 degrees Fahrenheit. Although that change may seem small, it represents a significant shift for such an extremely cold environment. Professor James Elliott of MIT suggested that these variations might reflect a slow warming process as sunlight triggers the evaporation of frozen nitrogen, temporarily thickening the Moon's thin atmosphere. Over time, that vapor may accumulate, forming a slightly denser atmosphere before eventually freezing again as Triton moves into its colder seasonal phases. During the long winter, the atmosphere may collapse almost completely as nitrogen freezes and settles back onto the surface. Despite these harsh conditions, scientists cannot entirely rule out the possibility of primitive life in a subsurface ocean. However, answering that question will require far more than distant observations from telescopes. Images from Voyager 2 and the James Webb Space Telescope provide invaluable clues, but they are not enough to fully understand Triton's environment. A dedicated mission would be needed to determine whether this distant moon truly hides an ocean and whether it might harbor the ingredients for life. One such mission concept, known as the Trident mission, was proposed by NASA as a possible journey to Triton. The spacecraft would have traveled for roughly 16 years before reaching the Neptunian system. Its goal was to investigate Triton's potential habitability, confirm the presence of a subsurface ocean, and search for molecular building blocks associated with life. The mission would also have mapped the remaining 60% of Triton's surface that has never been seen in detail, finally allowing scientists to assemble a complete geological map of the Moon. Unfortunately, the Triton proposal did not receive funding for a launch opportunity in the year 2021, losing the competition to 2 other mission concepts. Even so, Triton remains one of the most compelling destinations in the outer solar system, and many scientists believe that one day humanity will return to study this extraordinary world more closely. DCI Plus and Viridis. The upcoming missions that will explore Venus show that planetary exploration is far from slowing down. And for the mysterious moon Triton, all is not lost. China is currently considering a nuclear-powered mission to Neptune, which could one day bring a spacecraft into orbit around this distant ice giant and its largest moon. At the same time, it is still possible that NASA may reconsider the Trident mission for a future expedition. If such a mission is approved, Trident could reveal crucial information about ocean worlds and their geology. Explorations of Neptune's largest moon could either confirm or refute the presence of a vast subsurface ocean. And if such an ocean exists, scientists could begin to determine its approximate chemical composition, helping us better understand whether life could exist in the cold darkness of this distant world. The study of hypothetical and sometimes active ocean worlds, such as Triton, Mimas, Enceladus, or Europa, may completely reshape our understanding of the origins of life. These environments exist under extreme conditions beneath thick layers of ice, far from the warmth of the sun, yet possibly containing liquid water, chemical energy, and geological activity. Future expeditions will expand our knowledge dramatically. They will close many of the questions we ask today, while inevitably opening entirely new mysteries. Perhaps sooner than we expect, we will finally begin to answer some of the deepest questions in planetary science. How do global oceans form on icy planets and satellites? What processes keep these worlds geologically active for billions of years? And ultimately, the question that echoes through every exploration of the cosmos: are we alone? And all of this curiosity leads us back to one of the solar system's most mysterious moons, Triton. In the vast expanse of our solar system, among the swirling gas giants and the rocky Earth-like planets, there exists another intriguing world. A world larger than the planet Mercury, yet it does not orbit the Sun. Instead, it circles a colossal planet, Jupiter. This world is Ganymede, the largest moon in the entire solar system. Ganymede is wrapped in a thick shell of ice. For decades, its battered and scarred surface has fascinated scientists. The craters, ridges, and grooves etched across its frozen crust tell a story billions of years in the making, a story that humanity is only beginning to understand. Beneath this icy exterior, Ganymede hides secrets that could fundamentally change our understanding of life in the universe. It is currently the only known moon that possesses its own magnetic field, and deep beneath its frozen surface, scientists believe there may be a vast ocean of liquid water, possibly containing more water than all of Earth's oceans combined. Today, we take a journey to this distant world. We will examine the latest images, study the discoveries made by modern spacecraft, and explore the mysteries that Ganymede is slowly revealing to us. Our story begins more than 4 centuries ago. In the year 1610, a man named Galileo Galilei pointed his primitive telescope toward the night sky. What he discovered would forever change humanity's understanding of the universe. Through his telescope, Galileo observed 4 small points of light orbiting the giant planet Jupiter. These were the first moons ever discovered around another planet, now known as the Galilean moons. Among them was the largest of all, Ganymede. Galileo's discovery was revolutionary. It provided the first clear evidence that not all celestial bodies revolve around the Earth, challenging the dominant worldview of the time and helping ignite the scientific revolution. Today, we know that Ganymede is truly a giant among moons. Its diameter is about 5,273 kilometers, making it the largest moon in the solar system, even larger than the planet Mercury. But size is not the only thing that makes Ganymede extraordinary. Fast forward to the present day. and our ability to study this distant world has advanced dramatically. Modern telescopes, both ground-based and space-based, have provided increasingly detailed observations of Jupiter's moons. But it was the arrival of spacecraft missions that truly transformed our understanding. Probes such as NASA's Galileo orbiter and the Juno spacecraft have traveled to the Jupiter system and sent back detailed images and scientific data, allowing researchers to study Ganymede in unprecedented detail. These missions revealed a world of striking contrasts. Ganymede's surface is a patchwork of two very different types of terrain. Dark, heavily cratered regions record the violent history of ancient impacts. Meanwhile, brighter regions filled with grooves and ridges suggest a more dynamic and geologically active past. But perhaps the most fascinating aspect of Ganymede lies beneath its frozen surface. Scientists believe that deep below the ice exists a vast ocean of liquid water, a hidden sea that may contain more water than all the oceans on Earth combined. The spacecraft managed to capture remarkably clear and detailed images of Ganymede, giving us one of the most complete views we have ever had of this distant and fascinating moon. These images are not only visually stunning, they are also essential for understanding Ganymede's geology and its possible connection to life beyond Earth. Across its icy shell, scientists can clearly see a contrast between dark regions and bright grooved terrain. Subtle variations that reveal differences in the purity and composition of the ice. By studying these patterns, researchers can slowly reconstruct the long history of Ganymede's frozen surface, how it formed, how it fractured, and how it has quietly evolved over billions of years. The darker regions are believed to be the oldest landscapes on the moon, some nearly 4 billion years old. They are heavily cratered, marked by the scars of countless impacts, evidence that these terrains have remained largely unchanged for immense stretches of time. In contrast, the brighter regions tell a very different story. Here we see long grooves, ridges, and vast furrowed patterns stretching for hundreds of miles across the surface, some rising more than a mile high. These younger terrains suggest that Ganymede has not always been a frozen, motionless world. Instead, deep inside the moon, subtle forces may still be shaping its crust. One of the key processes believed to drive this activity is tidal heating. As Ganymede orbits Jupiter, the enormous gravitational pull of the giant planet causes the moon's interior to gently flex and stretch. Over time, this slow and rhythmic bending produces heat within the icy crust. That heat can crack the surface, shift the ice, and create the ridges and grooves we observe today. In many ways, it resembles plate tectonics on Earth, but unfolding in a much colder and far more alien environment. By studying these geologic features, scientists learn not only about Ganymede itself, but also about the wider diversity of icy worlds scattered across our solar system. And as our understanding deepens, one question continues to surface again and again. Could this distant, frozen moon harbor life? At the moment, we do not yet have a definitive answer, but several clues make the possibility difficult to ignore. Deep beneath Ganymede's thick ice shell, scientists believe there may exist a vast subsurface ocean of liquid water, perhaps more than 100 kilometers deep. On Earth, wherever liquid water exists, life often follows, even in the darkest depths of our oceans. Near hydrothermal vents where superheated water rises from the seafloor, entire ecosystems thrive in conditions once thought impossible. It raises an intriguing possibility. Could similar environments exist on Ganymede hidden far below its frozen surface? Beyond the reach of sunlight, quietly warmed by the moon's interior, perhaps small hydrothermal systems could exist there as well, releasing mineral-rich water into the dark ocean below the ice. If so, they might create conditions where simple life could potentially survive. Ganymede also possesses something unique among moons, its own magnetic field. This magnetic field creates a miniature magnetosphere around the moon, offering some protection from the intense radiation surrounding Jupiter. In addition, faint traces of oxygen have been detected in Ganymede's extremely thin atmosphere. While far too sparse for humans, such conditions might still allow certain forms of microbial life to endure. Much as extremophile organisms survive in some of Earth's most hostile environments. Of course, these possibilities remain speculative. Exploring a world nearly 500 million miles from Earth is not simple. Signals traveling between Earth and Jupiter can take more than 40 minutes to make the round trip, making real-time control of spacecraft impossible. Every probe sent to this distant region must operate largely on its own, navigating a harsh environment of intense radiation and freezing temperatures. And even after the data arrives, interpreting it is a slow and careful process. Each new image, each measurement, each fragment of information must be studied, debated, and compared with everything we already know. Our understanding of Ganymede continues to evolve. What we believe today may shift tomorrow as new discoveries appear. But that is the nature of science. Each answer leads to new questions. Each mystery solved reveals another waiting quietly behind it. In the coming decades, new missions will return to the Jupiter system. One of the most important is the European Space Agency's JUICE mission. The Jupiter Icy Moons Explorer. Launched in April 2023, JUICE will spend years studying Jupiter and its moons, eventually focusing on Ganymede itself. Its instruments will map the moon's icy crust, probe the ocean hidden beneath, and explore its unique magnetic environment in unprecedented detail. Beyond JUICE, scientists are already imagining even more ambitious missions. Landers that could touch down on the icy surface, rovers that might travel across the frozen plains, and perhaps one day submarines capable of descending through the ice to explore the dark ocean below. For now, those ideas remain dreams. But every great discovery in space once began the same way. With curiosity, with patience, and with the quiet determination to understand a universe far larger than ourselves. So as we reach the end of tonight's journey, Ganymede remains what it has always been. A distant moon, a frozen world, a quiet place orbiting a giant planet in the outer solar system. Yet within that silence may lie answers to some of the oldest questions humanity has ever asked. How do worlds evolve? Where can life exist? And how common might it be among the countless planets and moons scattered across the cosmos? For now, the answers remain hidden beneath miles of ancient ice, waiting, patiently, for the next generation of explorers to arrive. And perhaps, someday, when we finally look beneath that frozen surface, Ganymede will reveal a story none of us expected. Until then, the moon continues its slow orbit around Jupiter, silent, cold, mysterious, and if you are listening to this while drifting towards sleep, let that quiet rhythm of the solar system carry you gently into the night. The planets will keep moving, the moons will keep orbiting, and the universe will continue unfolding its mysteries slowly, patiently, far beyond the horizon of our dreams. Good night.